So in this video, we're just going to do a quick overview of the toolbox functions that we're going to be using in the remainder of the videos. So the first toolbox function is the function f of x equals x, or just y equals x. So this is just a basic linear function, and we call it a toolbox function because it's the simplest possible linear function that we can build, and it turns out that every other linear function can be built from it. You want to think about the basic characteristics of f of x equals x. Clearly its domain goes from negative infinity to positive infinity, as does its range. It's going down forever, it's going up forever, it's increasing over its entire domain. It has odd symmetry because it's a reflection of itself in the line, in the origin. We're going to be transforming toolbox functions, and what we're going to need to do is keep track of important points on the graph. So important points on the graph are, for example, intercepts, x and y intercepts. So here we see that we have an intercept at the origin, 0, 0. So that's going to be an important point on the graph. And then when we're doing graphical transformations of toolbox functions, the thing that we want to keep track of are nice points on the graph, or lattice points. So lattice points are just points on the graph for which both the x and the y coordinates are integer values. So this particular guy, f of x equals x, it's pretty straightforward to generate lattice points. You input a 1, well, what do you output? You output a 1. So the ordered pair 1, 1 is on the graph, and this is a lattice point because both numbers are integers. So we can plot that lattice point. Oh, it's like it's Sunday. We're making a Sunday video and it's turning out like a Monday video. In fact, you can eyeball the lattice points because y equals x. We're going to get lots of nice lattice points. Usually in the homework you're asked to graph at least 3 nice points on the graph. Intercepts if you can get them, lattice points otherwise, and then you're going to be asked to move those points around using graphical transformations, which we're going to be going over in later videos. So that's f of x equals x, the first toolbox function. Second toolbox function is the absolute value function. F of x equals the absolute value of x, and this is the function where you plug a number in and the function tells you how far that number is from 0. Domain goes from negative infinity to infinity, right? We can go as far this way as we want. Remember in the GeoGebra pictures, if I don't end it with a solid dot or an open circle, then we assume that it has arrows. So it's going to from negative infinity to infinity along the x-axis. So there's the domain. The range starts at 0 and goes to infinity. And it's increasing from 0 to infinity and decreasing, going down from negative infinity to 0 along the x-axis. It has even symmetry. It's a reflection of itself in the line x equals 0, or the y-axis. And this is easy to get nice points. At 0, the output is absolute value of 0, which is just 0. So we get the ordered pair at the origin. There's a nice point. If we were graphing, that's a point we could move. And if you put in plus or minus 1, you know that the absolute value sign is going to kill that negative, so you just get a 1 out. So when we input 1, we output 1, get the point 1, 1 on the graph. Input negative 1, the absolute value of -1 is +1, and we get the point -1, 1 on that graph. The next toolbox function we're going to be working with extensively is the squaring function, f of x equals x squared. The domain, -infinity to infinity along the x-axis. Again, there's arrows on this graph. The range of those starts at 0 and goes to infinity, so our outputs, we don't get negative outputs from the squaring function. It's decreasing from -infinity to infinity. Function's decreasing through here, increasing from 0 to infinity as we move up this way. Has even symmetry because it's a reflection of itself in the y-axis, and you can get nice points on this graph. Gives you the ordered pair 0, 0. So the origin is also the x and y intercept. You plug in a plus or -1, it isn't going to matter because we're squaring them. Whether you plug in a plus or -1 and square it, the output's going to be 1. So you can see we get nice lattice points here and here. For graphing, usually having 3 nice points on the graph is going to be good enough for what we're going to be doing. We could generate additional nice points by plugging in integer values to the function and getting additional lattice points on the graph. These are nice points. Square root function. Square root. Oh, there's a copy and paste mistake there, isn't there? And it's not letting me kill it for some reason. Looking for those copy and paste errors. Square root function, he's going to look like f of x equals the square root of x. Or another way that we can write him is f of x equals x to the 1/2 power, which is going to be the more useful way of writing this when we get into calculus. Square root function, you generate nice points by dumping in nice values like 0. We want to dump in perfect squares. So we get the point 0, 0 on the graph. Want to notice for this guy, his domain is from 0 to infinity. Next nice point on the graph, 1 is a perfect square, so the square root of 1 is 1. We get a nice point right here at 1, 1. And the next nice point on the graph, you would need to plug in a 4 because 4 is a perfect square. So when we plug in 4, we see that we get a 2 as an output. And those would be the 3 points in future slides or future videos. Those are going to be the 3 points on this guy that we're going to use consistently. Cubing function passes through the origin, has the point 0, 0, and we could calculate that. We could plug 0 into the cubing function. 0 times 0 times 0 equals a big fat 0. And then cubing a 1 is going to be a nice thing to do. F of 1 is 1 cubed, which is just 1, so we get the point 1, 1. And f of -1, these are going to be the 3 points we probably will use most of the time. -1 cubed is going to be -1. This function has odd symmetry. It's a reflection of itself through the origin. Input a -1, output a -1. So that's the cubing function, and he grows fast. This cubing makes things grow fast. So if we plugged in a small integer and tried to get another lattice point, I plug in a 2, it's going to pop out an 8. You can see we'd have to go up off the grid that I have available in order to plot that point. So cubing is going to make numbers grow a lot faster than squaring, for example. And then the last the last toolbox function that we're going to be using. Not the last in the sense that these are the only ones that there are, because there are infinitely many toolbox functions. But for the purposes of the next set of lessons, we're only going to use the toolbox functions that I'm giving you right now. We're going to be doing transformations of these toolbox functions, and we really want to understand these transformations, particularly if we're moving on into trigonometry, because we'll use function transformations to develop the formulas for trigonometric functions. The last toolbox function we're going to be using is the cube root function, and take the cube root of 0. So what number times itself 3 times equals 0? Well, that's going to be just a 0. So we've got the origin as our x and y intercept. The next nice number is going to be to plug in a 1, and the cube root of 1 is just 1, because 1 times 1 times 1, 1 times itself 3 times, gives you a 1. So we input a 1, we output a 1. F of negative 1 is going to be a nice lattice point, because the cube root of negative 1 is equal to negative 1, because negative 1 times negative 1 times negative 1 equals negative 1. So we get this nice point on the graph. Input negative 1, output negative 1. And the next nice point isn't going to happen until all the way out here at 8. We can calculate the cube root of 8, which is going to equal 2, because 2 times itself 3 times generates an 8. So we get the point 8. Input 8, output 2. We could also input a negative 8 over here, which would output a negative 2. Negative 8, negative 2. Those are the toolbox functions that we're going to be using through the remainder of the videos for this particular lesson.